So what I'd like to tell you about today is a project that several of us at Carnegie have begun over the last about year and a half or so, with the main goal of making large 3D maps of the intergalactic medium back at a redshift of about 2.5, which is also about 2.5 billion years after the Big Bang. And our main purpose for undertaking this project is to provide a new way to study galaxy evolution and how it depends upon the environment of galaxies, which I'll be talking about in this talk. So it involves a number of people that you can see listed here, and most especially Gwen Rudy and Guillermo Blanc, and then we also have a student at Pomona and undergrad, Sonny Rhodes, who's been doing some of the visualization work, and Victoria Perez at University of Chile, who's started working on this for her master's thesis. So I know this is a broad audience, and so I wanted to just begin with like the very big picture of at least what we're trying to contribute to. And one way I like to think about this is to just contemplate the huge range of galaxies that exist in the universe today. So there's at least a factor of 10 to the 10 in the mass of stars that galaxies have formed. And even if you look at galaxies of similar mass, there's a huge range of properties in terms of their sizes, shapes, star formation activity, and everything. And yet, when we look in the early universe, for example, the little density fluctuations that are present in the microwave background, then the initial conditions are pretty simple, comparatively speaking. So this is like a Gaussian random field, basically. And so one way to view the sort of overarching goal of studying galaxy formation and evolution is a way to, an attempt to understand the physics that takes us from these simple initial conditions to this huge diversity of properties that we see around us today. Now, when we study an individual galaxy, we don't have access to what its initial conditions of formation were. So there are two properties that are related to the initial conditions that have often been used. Those are a galaxy's mass and its environment. Mass is relatively simple to understand. It could be the mass of the stars in the galaxy. It could be the mass of the dark matter halo that the galaxy is embedded in. Environment means different things to different people, but broadly what it's trying to get at is sort of what is the density on scales beyond the galaxy itself or beyond the dark matter halo of the galaxy. So classically, it's often been measured by looking at the number of neighboring galaxies. So for example, you can see isolated galaxies don't seem to have any neighbors. Most galaxies are in kind of loose groups, like Milky Way is, and the galaxy clusters are the richest environments. And both of these properties are clearly important because they correlate with basically all observable properties of galaxies. Shapes, sizes, star formation rates, and so on. This has been known for quite a while. So this is going back to 1980, some work showing how the morphologies or shapes of galaxies vary with the local density. So what this plot shows is if you divide the galaxy population into the spirals, the ellipticals, and the S0 or lenticular shaped galaxies, there's a very strong dependence on the fraction of the galaxy population with the environment, which in this case is the density of nearby galaxies. So the ellipticals and the lenticulars are much more prevalent in the dense environments. For example, this has been known since at least 1980. Often it's kind of difficult to tease apart these two important properties of mass and environment because the mass distribution of galaxies is different in different environments. But now that we have very large data sets in the local universe, for example, like the Sloan Digital Sky Survey, it's possible to tell that some important properties of galaxies clearly depend on both the mass and the local environment. So this panel shows the fraction of galaxies that are red, or I usually call them quiescent galaxies. These are galaxies that are devoid of star formation. And for any galaxy mass, there are more of these in denser environments. And in any environment, massive galaxies have a higher fraction that are red. So it's not only that one of these properties matter. Clearly, they're both important. So how does the environment of a galaxy actually affect its evolution? This can be a very multifaceted problem. There's one simple way, which just comes from our understanding of how structural formation occurs and the kind of concordant cosmology. That tells us that if a galaxy is embedded in a large-scale overdensity, it will reach the critical density to collapse earlier. And so, in a sense, the clock is different for galaxy formation in different environments. In a denser environment, the clock starts earlier, and it might also kind of run faster. Separately from that, there are also specific physical processes that can only occur in dense environments. Some of these involve the gaseous medium that's present in dense environments. If a galaxy is passing through a hot, kind of a high entropy gas, that can remove the gas from the galaxy, which deprives it of the fuel it needs to form new stars. It can also be cut off from the cosmic web and unable to accrete new gas. This is called starvation sometimes. In a dense environment, galaxies interact with each other more. They can either have close encounters, which is sometimes called harassment, or they can actually merge and coalesce. And we kind of know all of these things happen. You can point to specific examples of all of these processes in action. So the question is more how important they are, and how important they are compared to internal processes for shaping how galaxies have evolved in different places and different epochs in the universe. So to make it a little more concrete, one observational question that we're trying to get at is, when did the environment start to matter for galaxy evolution? If we know that, that's very helpful because we can look at the physical conditions that are present when the environment started to affect galaxy evolution, and we'll know something about the time scale that the processes are acting over. So in order to do that, we need to do look-back studies and look at distant galaxies and try to tease out when the environmental effects set in. And to do this, it's often been the case that people have studied galaxy clusters, which are these extreme overdense regions in the universe, not because they're the only place where the environment matters, but because they're the extremes, and so they're easier to locate at higher redshifts and enable these kind of look-back studies. So this is just an image of a galaxy cluster in the relatively local universe. Back at a redshift of 1, about 8 billion years ago, I think the state-of-the-art is the Sparks and G-class surveys. These are, well, actually, it's kind of hard to see the red here, but they studied a number of galaxy clusters around a redshift of 1. And what they found was that these mass and environment correlations that we see locally were already present by a redshift of 1. And the main difference between galaxies that are in these clusters and those that are not is the fraction of galaxies that are of this quiescent or red and dead type. If you look at the stellar properties in just the star-forming galaxies or just those that are non-star forming, they're fairly similar whether galaxies are in clusters or not. But there's a big effect on the division of these two populations. And they interpreted this as evidence that the environmental effects clearly were already present, and they must have operated fairly quickly because you don't see this transitional type very much. Now the frontier for finding the earliest galaxy clusters is redshifts of about 1.5 to 2. There's just sort of several of these that have been found and confirmed to be really massive structures. I worked on one of these, and they're really a mixed grab bag that have been located via different methods. Some of them by looking at infrared colors of galaxies, or by seeing X-ray emission from hot gas in the cluster, or by using what are called biased tracer techniques. These are basically looking for types of galaxies that might be kind of signpost for cluster environments. For example, looking around radio-loud galaxies. So we have really small numbers right now, and probably as a consequence of this, you can find many conflicting results on how galaxies might or might not evolve differently in these really early dense regions of the universe. So you can find claims that there was no environmentally dependent quenching. This is the shutting down of star formation to produce those red and dead galaxies. That was not effective beyond a redshift of about 1.5. And on the other hand, there are examples of clusters at higher redshift that have very high fractions of galaxies that are red and dead. Some people think that galaxies are growing quicker in size in these dense regions. Maybe they have more galaxies to merge with. Others haven't found any difference. The metal content of galaxies in dense regions might be enhanced, or it might not be. And I think the bottom line is we don't really have enough of these structures to tell right now. So, I think it was Adam Muzzin at a conference that pointed out, it's like trying to study galaxy evolution when you have like 5 galaxies. What could you say? You would just say some of them are blue and some of them are red, and that's about all you could probably really get at. And so we're kind of in that situation now with these early clusters. Now, as you go to higher redshifts, beyond a redshift of 2, say about 10 billion years ago, then the nomenclature shifts slightly. People tend to refer to proto-clusters. So the distinction that they're getting at here is that a cluster is kind of a thing that's sort of collapsed and virialized. The proto-cluster is this more diffuse, extended structure that will eventually become a cluster, but is not really yet fully collapsed. And locating these, a number have been located, but it's a pretty hard business. You can see these are images from a dark matter-only in-body simulation. There's a cluster at redshift 0. You can see its progenitor at earlier and earlier times. And you can even identify these things all the way back to the first billion years. But it becomes harder and harder. Of course, the galaxies are getting fainter. The density contrast is going down. And the angular sizes that are involved are really huge. So these protoclusters at a redshift of 2, you can see compared to the full moon, kind of have a comparable size. So it's just in terms of an observational challenge, that's perhaps foremost. So what are some ways that, even though we can't confirm it yet, that we think galaxy evolution might proceed differently in a dense environment like a protocluster, redshifts of 2 and higher? Sort of the most baseline expectation that I would say almost has to be present is what I referred to earlier, that structure formation is accelerated in dense environments. So you can think that that's likely to lead to galaxies that are kind of older and more massive because their clocks started earlier. And that's been seen in some systems. This is a cluster at redshift 2.3. You can see this spike of galaxies at a given redshift, many of which are older than the ones that you'll find at nearby redshifts that are not in the protocluster. So that's kind of the baseline, but then there could be some processes that are really only operative in these dense regions and produce other effects. So for example, the galaxies might be merging more frequently in a high density region. The gaseous medium that the galaxies are embedded in, probably rather unique in a protocluster, might be more metal enriched, might be kind of more multi-phase as it's polluted by the outflows of all these galaxies. And there's another theoretical expectation that protoclusters might be might be the best place to test. This has become a fairly important paradigm, I would say, in galaxy evolution theoretical work, which has to do with the way in which galaxies acquire their gas. So in low mass halos at all times, in this model, accretion is primarily cold. That just means that galaxies are able to acquire gas through filaments connected to the cosmic web. The gas can accrete directly onto the galaxies without ever being shock heated. But in more massive halos, it's more complicated. It depends on the mass and the time. So at earlier times or in lower masses, it's thought that those cold filaments are able to penetrate a hot halo and feed the galaxy with gas that it will form stars with. Whereas at higher masses and later times, it's thought that all the gas will shock heat, and so you'll just have this hot halo, and this could have profound implications for the galaxy evolution because the galaxy can be starved of gas if it's all in this hot phase that takes a very long time to cool. And so these are just some hypothetical implications that Overzier compiled for what we might see in these two regimes. And the critical point for this talk is that between about a redshift of 2 and 3 and the progenitors of today's clusters is right at this boundary where there might be kind of a transition happening. And so the protoclusters could be a good test bed for this model. And the final thing that could be quite different about galaxy evolution in dense environments is a suggestion by Caitlin Casey, which I think is really interesting. And she pointed out that there's a lot of these protoclusters that have a huge number of very dusty, highly star-forming galaxies, which are rare and thought to be pretty short-lived, like 100 million years or so. And if you were to calculate what the probability is to find these rare things, if they're just all kind of triggered independently, and their lifetime is short, then you should almost never find more than 5 or so. And yet there are a number of examples where you see a dozen or more. And so her suggestion was that the fact that you have these rare objects that have a short lifetime dispersed across a very wide area, a much wider area than over which galaxies could directly influence each other, that it suggests that the really large-scale environment, like 10 megaparsecs or so, is directly causing this. Like perhaps there is some common tidal field that's funneling gas into all the galaxies, or some filament collapsing. Don't really know. But this would be, if this is the correct interpretation, it would be sort of the most dramatic effect of the very large-scale environment on individual galaxies, I would say, that's known. So that's a little bit more speculative, but I think pretty interesting. So now I want to talk a little bit about how we actually map the environments at high redshift and find these proto-clusters and their inverse, which would be large voids that are underdense in matter. So the workhorse method by far has been using the density of galaxies to trace the matter density. And this is a very effective method. It's been used to find virtually all of the structures that we know at high redshifts. So this is just one example of a large structure that was found in a big spectroscopic survey. But there's some difficulties. You can use photometric estimates of the redshifts, but that blurs out the structures because the errors are much bigger than the size of the structures. Spectroscopic surveys tell you redshifts very exactly, but it's pretty hard to get the density you need to actually trace out the whole matter field at the level of detail you would like. So even in a very large effort like this VIMOS Ultra Deep survey that consumed many nights on the VLT telescopes, the galaxies are still separated by a distance that's comparable to the size of the biggest structures, so it's not ideal. And there's also the concern that you might kind of be biased in what you find by targeting only certain kinds of galaxies. So we're going to have a totally different method very soon, which is to look at in the microwave background for the signature of hot gas via the Saniev-Zeldovich effect. The CMB maps haven't really been sensitive enough to find structures redshifts approaching 2 until the latest generation of receivers. So like the South Pole telescope should find kind of tens of clusters, about redshift of 1.8 or so. But it falls off really quickly because the whole method is premised on the presence of hot gas. And that requires the structure to be kind of more evolved and collapsed. The method that I'm going to talk about is quite different in that it uses neutral hydrogen in the intergalactic medium in order to trace the density field, which is dominated by dark matter, on large scales. So we detect the hydrogen by looking at the absorption it produces in the Lyman-alpha line, which I'll show you in a minute, in the spectra of background objects. And on large scales, the connection between the neutral hydrogen and the dark matter is fairly straightforward, and so it provides a nice tracer of the density field. This has a few advantages over the other methods. So every galaxy now that you observe doesn't just tell you about its own neighborhood. Because you're looking for the absorption by this gas in the foreground, it tells you about the matter for like 400 megaparsecs in front of the galaxy. And that means you only need to have a high 2D sampling of galaxies on the sky, not a high 3D sampling that you would need if you use the number of galaxies itself to measure the density field. So that enables you to make much higher resolution maps than you could otherwise do. You can connect this to the mass of the structures that you're seeing. Usually we don't have a very good idea of the mass because they're not virialized, and so the dynamics are hard to interpret. So that's very nice. And it is independent of the galaxies that are in the structures you're finding because you're not using them to find the structures. You're just seeing the gas in the structure and absorption instead. So this is a little, you have many experts on the IGM here, and so many of you are probably like quite familiar with this, but nonetheless, this is a little animation that demonstrates the concept. You have a quasar on the left, which acts as this bright backlight, and you're going to see, this is the spectrum of the quasar, and you're going to see as the light traverses the intergalactic medium between that quasar and the observer, you see that gas imprints this absorption at the wavelength of Lyman-alpha and provides a very detailed map of the matter distribution along this one narrow pencil beam or skewer. There's also absorption at other Lyman transitions, which is not going to be really relevant for this talk. So this is the basic method, and the traditional backlight of choice has been to use quasars because they're super bright. You can see them to great distances, and you can get beautiful spectra that tell you with very high fidelity the distribution of hydrogen and metals along one line of sight toward that quasar. For our method, the method we're using is a little distinct because instead of using quasars, we're primarily using galaxies as the backlight, as you'll see. And we don't obtain very detailed spectra of the individual objects. We obtain very noisy spectra, but we have many different sight lines instead of just one, and that enables us to try to reconstruct the three-dimensional distribution of matter. So in order to kind of help you visualize this, I'm going to show you some mocks. So this is taken from an in-body dark matter-only simulation at a redshift of about 2.5. And what you see here is a cross-section at a given redshift through that, and the colors tell you the transmission of Lyman-alpha, which is related to the matter field at this redshift. So in this color scheme, the blue and black are overdense regions, and the red are the underdense regions. Now, if we were to observe all the quasars that are in a volume of this size, which is about 1 square degree, there would typically be about 30 of these in a modern quasar survey, like, for example, the Big Boss. And so you can see how these 30 sources would sample the density field. And we can then ask if we were to kind of simulate the observations we could obtain of these quasars and use all these distinct sight lines to try to reconstruct the three-dimensional matter distribution, then it doesn't look very good. Like, this is basically edge effects, so it's really bad. This is a little bit deceptive, actually, because it is possible to find large structures using only a Big Boss-like survey, but you miss a lot of things because the separation between your different sight lines that you're shooting through the density field is really big. The advantage of going to galaxies as the backlight is that you have a tremendously larger, by more than an order of magnitude, number of sources that you can observe. The difficulty is that they're a lot fainter, so you can't get beautiful spectra, but you have many, many sight lines, perhaps about 800 through a volume like this one, and now the level of detail you can see in the map is a lot higher because your skewers are now only separated by a few megaparsecs instead of like 15. So, yes, so we attempt to observe quasars in addition to galaxies, and they provide a good cross-check. We haven't looked into that in great detail yet, but that's the goal, yeah. So if I overlay the truth, since this is the simulation, on top of this mock observation, you can see what you can expect to do. You can't see all the tiniest structures, but the overall large features you can recover. So that's promising. And this is basically the strategy that we have implemented in this survey that we've started at Carnegie called LATIS. So that stands for the Lyman-alpha Tomography IMACS Survey. IMACS is the spectrograph that we're using on the Magellan telescopes, Las Campanas in Chile. And the goal of this project is to map the intergalactic medium at redshifts of 2.2 to 2.8 using the Lyman-alpha absorption method that I've just described over an area of about 2 square degrees, which gives us a pretty large volume that you can see here. And we think this is going to take about 3 years and about 58 nights, and we're about halfway through that right now. And we're just starting to get our first really large maps. And again, the overall goal of this is to use it as a probe of galaxy evolution in different environments. So there's another group that you may be familiar with because they're using Keck called Clamato. They were actually the inspiration for this project. They're using LRES. This is led by KG Lee and his collaborators. And they've had a data release. They've covered about 1/6 of a square degree. And what we're doing is similar in terms of like the resolution of the maps and the kind of galaxies we're observing. We're just trying to do it over a much larger volume so that we can get a kind of statistical sample of over and under densities. So our main goal, as I mentioned, is to look at environment-dependent galaxy evolution in this new way that's based on the IGM. So there's 2 prongs to this approach. The first is, of course, to map the large-scale structure, as I've just described. So these will be the largest maps with kind of megaparsec resolution of the distant universe. We're distance redshift 2.5. And that will provide kind of 2 things. One is that for every galaxy within this huge volume, you'll have a low signal to noise measure of the density field on megaparsec scales. And at much higher significance, you can detect extended over and underdense regions. For example, proto-clusters, as I've just been describing. And you'll see some examples of that in a few minutes. We want to correlate galaxy properties with their environments, and many of those properties we can get from the same spectra that we're using to probe Lyman-alpha absorption. So we're getting nice rest ultraviolet spectra of galaxies down to slightly below L star, and that will tell us about things like the ISM in these galaxies, winds, perhaps even some of their stellar properties. And the other key point is that we're executing this program in fields that are very well studied, and a lot of large telescope time has been invested in. And so there's a lot of spectroscopy of galaxies that's already been done by various groups, including, for example, like the MOSDEF at UC. And we'll be able to leverage this kind of legacy spectroscopy by adding this new environmental measure. So for the any aficionados of kind of surveys and observation in the room, I just have a couple of slides on how we're actually doing this. We're using the IMACS Spectrograph that you see here. Its big advantage is that it has a field of view of about 1/6 of a square degree. And that is what really enables us to make these big maps. In order to improve the sensitivity in the blue wavelengths where there's Lyman-alpha, we put the more blue-sensitive mosaic at the wide field focus. This instrument has 2 foci. We have a new GRISM that's kind of optimized for blue throughput. And we have a custom filter that we use that enables us to observe about 300 galaxies simultaneously. We're doing this in more or less 2 fields. One is the Cosmos field, many of you may have heard of. We're observing about 0.85 square degrees there. And in the fall, we're observing 2 fields of the CFHD Legacy Survey. And collectively, these overlap many other surveys that you can kind of see listed here. This is a tiling of 6 IMAX pointings within the Cosmos field on top of the areas covered by some other large surveys. We need to get to a signal noise of 2 in the forest, and this takes a long time, like 12 hours, but we're getting 300 spectra at once, so we don't feel too guilty about it. And we're primarily targeting relatively bright sources for these redshifts down to the magnitude limits you can see here using photometric redshifting and color selections. And basically, we're observing about half of the galaxies that are brighter than L star in this redshift range of about 2.2 to 3.2. So that's a little on the kind of mechanics of what we're doing. Oh, and we also include quasars, as I mentioned before, but they're only a few % of the objects. It's mainly a galaxy survey. So we're about halfway done currently. We have just over 2,000 spectra of galaxies beyond redshift of 2.2 over about 1.3 square degrees. About half of that is totally done, and the other half of the area we have partially completed the observations. So this is just kind of a fun graphic showing the spectra ordered by redshift, and the color coding is the intensity. So you can see the redshifting of these various ISM lines, and also the forest between Lyman-alpha and Lyman-beta up at the top there, which is our primary interest. And we're kind of pretty much on track now to finish after 3 years. So the name of the game here is, instead of using quasars, as has typically been done, we're using galaxy spectra to look for fluctuations in the Lyman-alpha forest. And I think this is actually easier in many ways. There's a long history of how you estimate the continuum and look at the absorption in quasars. Galaxy spectra, I think, are actually kind of easier. So this shows the median spectrum from our whole survey. And you can see all of these strong lines that are ISM and wind lines. There are a lot of weak features here, some of which are from the actual stellar photospheres. And all of that is what we will ultimately use to look at the galaxy properties in different environments. But the main subject of this talk is the Lyman-alpha forest region. And you can see that there's a few lines in galaxy spectra in the forest that you can kind of just mask out and ignore. Overall, the spectrum is pretty featureless, which is really nice. So this shows a few example spectra from the survey. The thick lines are models that we have made, kind of simple models where we combine, basically we've made template spectra by averaging galaxies with different Lyman-alpha strengths and sort of match the continuum shape to each galaxy. And the actual measurement of interest for all of the rest of the talk is actually the fluctuations you see around these thick lines that are the models. Those are the fluctuations in the Lyman-alpha forest. And they're usually written in terms of this delta F parameter, so that tells you the flux that's transmitted relative to the mean at that redshift, or more visually, it's the data, the noisy thing, over the model, the thick line. And as you can see, this is like a very noisy business. The signal to noise is kind of comparable. You know, a lot of these fluctuations are just noise. But the key thing is that because we have many different neighboring sight lines, when you see downward or upward fluctuations in lots of sight lines in the same patch of the sky, then it starts to build up the signal to noise, which you'll see in a minute. So the most important number when you're trying to do this kind of Lyman-alpha tomography is the density you have of sight lines, because as you can imagine, it's not possible to find features that are smaller than the separation between your galaxy spectra. So the kind of mean separation between your sight lines governs the resolution of the map that you can ultimately make. And so that sight line density is shown here, the actual aerial density, and then on the right is the corresponding mean sight line separation and co-moving units. And our fields are the various lines. The thick one is the Clamato group. So typically we're able to get kind of 2.5 co-moving megaparsecs, which is about 1 physical megaparsec of these redshifts. And it's not uniform. You can see the positions of our different sight lines, and they're clustered, and so there are gaps. There are bright stars sometimes that you can't observe near, and so that has to be taken into account ultimately in the analysis. So you saw this plot before. This is kind of like if you knew the coordinates of each line in this plot, you'd have the whole data set, basically. But so far I've just talked about individual spectra. And what we want to do is convert all of these 2,000 spectra into a three-dimensional map. So that requires some mathematics. So far we're using a method called a Wiener Filter, specifically this code written by Casey Stark. And the most important thing to know about it is that it takes a signal covariance as the input. Basically, this is a method to regularize the map so that you don't have features on scales smaller than the sightline separation, which you can't see. And so, as I mentioned before, our resolution's like a few co-moving megaparsecs, 1 physical megaparsec. So we've applied this method to all the data we got as of just about a week and a half ago, which was the end of our last observing run. And this is our first map in the Cosmos section of the survey. So this is the side-on view, and this is a 3D view. Red here are the matter overdensities, and blue are the underdensities. And you can see that it's not homogeneous at all. Like the IGM is very rich in structure, as we would expect from our model of cosmology. The middle of the volume is very rich, as you'll see, and you can actually trace out filaments and things like this. So this is already the biggest 3D map of the IGM with kind of megaparsec resolution, as far as I know. And I think this is kind of hard to visualize. I prefer to look at cross sections, so I have a movie for you. Let me kind of prep you with what this means. So we're going to be scanning through Redshift. The transverse area here is about 2/3 of a degree on a side. There's no data in this quadrant, so it's going to stay the same color. Red means a matter overdensity, and blue means an underdensity. And then, separate from that, the positions of galaxies, just from the redshifts that we measure, are these various dots. So you should be seeing dots broadly aligning with the red regions if this method is working and successfully digging out signal from these noisy spectra. So I'm going to start the movie now. This is at Redshift 2.2. So we're looking at the front of the volume. This part is relatively poor in structures. You see actually a lot of blue. You can see a number of things that kind of snake across because you're looking at these very extended structures at an angle. Now we're approaching the middle of the volume of the survey, which is very rich in structures, as you'll see, very extended one. These are over tens of megaparsecs, so we're looking at multiple proto-clusters, basically, in the map as a whole. You can see a whole lot of dots following these extended red overdensities. So we think the method is working pretty well. There's a part coming up momentarily where you can see galaxies snaking between two underdense regions of the IGM, which I quite like, in a few more moments. Right there, in the upper left. And now we're approaching the back of the volume at redshift of 2.8. There's another system of structures here. Basically, the back of this is just set by the fact that there aren't enough bright galaxies at higher redshifts to really continue doing the map.
What's the error bar here on a given density?
Yeah, so the typical position in the map, it varies spatially, but the typical position in the map, the measurement error is about half of the intrinsic variance in the IGM on these scales. And that is, the actual number is highly sensitive to the smoothing scale, and I can't remember it exactly. But essentially, it's kind of signal noise of 2 in an individual pixel, basically. But when you see very extended structures, it's clearly more significant.
Does this average
Yep.
to 0?
Yes, this map averages to 0, yeah.
Is that an absolute or is that a normalization?
That's pretty much by construction. So this is normalized to be deviations relative to the mean so that it's oscillating around 0. We can't actually easily measure what the mean is, so we actually take that, in fact, from George's work in order to normalize this. Okay, I'm trying to get past the slide. There we go. So I just want to show you a few of these big structures that you can see whizzing by in the movie. These are the most significant overdensities in one subchunk of the map that we've looked at more. So for example, if we look at this structure, one of the nice things about this method is that you can get a 3D map of it. So this is showing cross-section through each of the 3 axes centered on that overdensity. And you can overlay the positions of galaxies on it, and to first order, they trace each other pretty well. There are some interesting exceptions that we're looking into, but could be where the most interesting results actually are. This is back to the same 5, and you can see that there's some of them that are very rich in galaxies, and others that aren't really. So we were interested in that because my first thought was this is some spurious peak in our map, and it's not overdense in galaxies in any obvious way, so maybe we've done something wrong. So you can test that by zooming in on this structure and looking at each of the sight lines that's piercing this overdensity. So in this map, you see the circle and the overdensity that crosses the position of all our sight lines, and then these are now the spectra that are of the galaxies that are behind this overdensity. And the redshift is indicated here, and you can see that the individual galaxies are noisy, but actually all of them have a negative fluctuation there. So we're pretty sure that this is actually a real feature, even though it's not super rich in kind of L-star LBGs. We don't know what that means yet. It could be that the dominant galaxy population is something else. For example, quiescent galaxies or something. We don't know yet. But it's not the case that the maps are dominated by like a single strong system. It generally turns out that the features have some contribution, some small contribution that averages out over many individual spectra. So this is a low signal to noise game, as I mentioned. So one way to visualize that is to look at the values of our spectra versus the values of our map. So the black histogram here shows the fluctuations in the Lyman-alpha forest in all of our individual spectra combined into one histogram. And the blue is what you would get if you just had random noise. And you can see that basically it's the same distribution. So if you look at that, it looks like there's no information basically in the maps. But this isn't true, of course, because it's the spatial coherence of these noisy fluctuations that are producing the signals in the map. So if now we look at the fluctuations in the map instead of in every individual sight line, that's the black histogram. And the blue is what you would get if instead of putting in our data, you put in random noise. And now you can see that it's definitely broader. So there are structures that are found, and the reason is that it's purely the spatial coherence of these noisy fluctuations. Another nice thing you can do is to find underdense regions. This is actually really hard to do with a galaxy survey because if you don't see galaxies in some volume, it could be that it's an actual underdensity, or it could just be that you've only subsampled a part of the galaxy population and you just didn't pick any there. So the blue peaks here are the biggest voids in our map so far. And I think those will be really interesting also, both for looking at galaxy evolution stuff, and also there's potentially some cosmology you can do. So we intentionally started out by looking at one of the probably the most well-studied area of the sky, the very center of the cosmos field, where there's been all this investment of large telescope time. And so many of the structures you've been looking at in the IGM actually have known counterparts and have been detected already by other types of tracers. So for example, there's this very well-known structure, Redshift 2.44, that's been detected previously via all these different methods. And that turns out in our maps to be the single strongest feature, so that's reassuring. There is, for example, a proto-cluster at redshift of 2.5 with a very high star formation rate density, like several thousand solar masses per year within a small volume. It's detected in X-rays, so it probably already has some hot gas in it, and this also is detected on our maps. It's one of the strongest features as well. So basically, we're just scratching the surface of this, investigating the correspondence of the IGM features and the structures that have been detected by other tracers, but preliminarily, there are many correspondences that'll be interesting to look at. So we started to do kind of mock surveys, and that's extremely valuable to be able to interpret the signals you get in these maps. So for example, as you saw, you don't have convenient separate, like a grid of galaxies. They're kind of clustered and there's gaps. And so in order to be able to know whether a given feature in your map is real or not, it's very helpful to have some kind of simulated mock observations to compare to. And so we've been doing that by taking subvolumes of a very large dark matter-only in-body simulation and simulating the observations with the exact positions of galaxies that we have, the exact signal to noise in our observations, and using that to measure the significance of the things that you've been looking at, and also to be able to start weighing these overdensities that we're finding. Since, as I mentioned at the beginning, one of the main advantages is that you have some information on the mass of the structure. So the very first order thing you can do is to just look at a histogram of all the fluctuations in our map. You actually already saw this earlier in the talk, the black line. The blue, again, is what you would get from random noise. And now the green lines are if we do mock observations of different subvolumes of an in-body simulation. And so basically the takeaway from this slide is that the black is within the envelope of all these green mocks. And so the structure in the map at the level of this kind of most simple statistic is consistent with what we'd expect for lambda CDM. So that's also reassuring. We can now put some kind of confidence level on the different structures you've been seeing. So these are, again, sort of the top 5 within one subvolume of the map. They're kind of 5 to 8 sigma, so very secure. Now, the other thing that using the simulations is very useful for is measuring the masses of the structures. So this panel shows essentially what we've done is to create mock observations of these subvolumes, and the x-axis here shows the fluctuation in the Lyman-alpha forest in the map that we would get, and the y-axis shows the actual matter overdensity within that same voxel of the map. Since it's a simulation, of course, we have access to the true matter overdensity. And not surprisingly, there's a strong trend for a higher matter overdensity where there is more absorption of Lyman-alpha. More importantly, the scatter isn't huge. So that means we can hope to recover some good masses from this type of observation. So how that would work in practice, for example, if we go back to this overdensity that you've seen a few times, because of the nature of this method, you kind of get a 3-dimensional rendering of it. So for example, you can take this outer contour and integrate out this relation and get a mass of the whole thing. And if you do that in this case, you get about 10 to the 14.4. And so that's a clear indication that this object actually is something that's going to become a galaxy cluster at later times. And the masses are really useful if you think back to the panel I showed at the beginning about how we think the mode of gas accretion might be changing at different masses and redshifts. We need good estimates of the mass to be able to test things like that. So this panel shows you like how good of mass you can hope to get. This is in the mock observation, the mass that comes out compared to the true mass on the y-axis. And essentially, things that are above about 10 to the 14 solar masses, you can do a pretty good job of. It's pretty tight. We expect in the full survey to find about 28 structures with masses above 10 to the 14. That's what a lot of people consider the definition of a protocluster to be. About 10 of them will be the most massive things above 3 times 10 to the 14. So another thing that's kind of interest is the fate of these structures that we can find. In a simulation, you can look at the descendants of these objects, redshift of 0, present day, and that was done by Lee et al. This panel shows the mass that you measure via the method I just described, a redshift of 2.5, and this is what the mass is going to be at redshift 0 on the y-axis. And there's a trend. There's a lot of scatter because the assembly histories can be different. But there's kind of two takeaways I would make from this plot. So anything that's going to be a galaxy cluster above 10 to the 14, excuse me. Sorry, that's not, let's start on this one. So anything that we detect with the tomographic mass above 10 to the 14 is likely to become a galaxy cluster. Pretty much everything to the right of this line becomes a galaxy cluster. So all the things that you've been looking at basically are likely progenitors of clusters. The other thing is that there are many things that you can't detect at lower masses because they just haven't collapsed enough yet, basically. But things that will become massive galaxy clusters are almost all detectable at redshift 2.5 by tomography. So basically, when we detect things above this mass, they'll be protoclusters, and we should be pretty complete for the more massive protoclusters. So that's basically what our goal is, in part. This shows the contribution that this kind of survey can make to the overall number of these protocluster regions that have been found. This is a compilation and a review by Overzier. It shows all of the protoclusters that have been spectroscopically confirmed and have some estimate of the mass that says they're going to be above 10 to the 14 at the present day. And you can see between redshift 2 and 3, there are on the order of 20-something of these. And I said we were going to find 28 of them in Lattice. So it's kind of comparable to the total number of confirmed protoclusters that have ever been found. But homogeneously selected in a blind survey with information about the mass and independently of the galaxy populations in the protoclusters. So we think this will be a really nice way to look at galaxy evolution in the most dense environments. So far, we have focused our efforts on making these maps that you've seen. We're just starting to actually do the second half of our goal and look at how galaxy evolution differs or does not in different environments. So we've started looking at how the Lyman-alpha line is different depending on the megaparsec scale kind of overdensity the galaxy is embedded within. This is important for cosmology projects like HET-DEX that are using Lyman-alpha emission to do cosmology at redshifts greater than 2. Look at dark energy and so forth. We're starting to look at the variation of galaxy properties with the environment. I mentioned that we have these UV spectra, so we can look at things like winds and AG infraction, maybe even get at the stars by stacking spectra. And then we're hoping to work with the MOSDEF group to add the near-infrared dimension to this. We're looking at metal absorption in protoclusters with carbon-4 for the sort of first time to look at the dispersal of metals in these rich structures at redshift 2 and higher. And we're starting to look for the red sequence to see whether there's already quenching of star formation has already set in or not in dense environments. And then there may be some cosmological applications of this too, which we're just starting to look in with the help of Simeon here. So just to conclude, I know many people here are thinking about and excited about extremely large telescopes. And this is an area that I think is just dramatically helped by having facilities like this. So, for example, to illustrate this, I'm going to show you a simulated Lyman-alpha flux field exactly the same as the one you saw toward the beginning of the talk. And this is the kind of fidelity of reconstruction we can do with current surveys, like Lattice or Clamato or what the Subaru prime focus spectrograph might do. They're all getting about the same kind of density of sight lines, and so this is the kind of detail that you can expect to get. Going fainter helps dramatically, because if you just go a magnitude fainter, which is basically what you get with these extremely large telescopes when they're seeing limited, then you have 10 times more galaxies, more or less. So your resolution is improved by a factor of 3. And so now, instead of just tracing out these kind of largest features that are apparent, you can do something like that, which I think is really pretty amazing because, you know, it's almost a duplicate of the left panel. You can trace out all of these filamentary structures. So you're not just limited to looking at proto-clusters and big voids like I've been talking about. You can really look at kind of the whole range of galaxy environments. You can characterize them not only by the overdensity, but by kind of, you know, whether they're in a filament or a node, or kind of look at the topology of the large-scale structure at these redshifts. So this, I think, is really exciting, and it can be coupled with work that's focused in on sort of the inner circumgalactic region around galaxies, where the ability of these telescopes to access faint sources will provide, you know, a lot of new constraints on the gas on smaller scales than I've been talking about. So if you're interested in this stuff, we wrote a paper, white paper for Astro 2020 about how you can combine this kind of large-scale H1 tomography with studies of the circumgalactic medium and also very high-resolution studies of the galaxies themselves using the laser adaptive optics facilities of the ELTs. So that's it. So just to conclude, this has been about the Lattice project. We're making the largest kind of physical megaparsec scale resolution maps of the redshift greater than 2 universe by mapping the IGM in 3D. We hope that these maps will provide a fruitful new way of looking at galaxy evolution and how it depends on environment in the first few billion years, and also for identifying and getting masses of significant samples of proto-clusters. And this is an area that I think will only become more exciting as we get more capable facilities in the future. So thank you.
So I have two questions. First question is that what's the assumption you made when you are smoothing the density? Is in the 2D or 3D? And are you using the Gaussian or?
Yes, so there are many ways you could think about doing this. Right now we're just doing a very simple thing, which is that is essentially a 3D Gaussian that's isotropic. There has been work that's looked into using kind of a matched filter that, you know, is cosmologically informed, for example, to find specific things like proto-clusters. And it basically turns out not to make a huge difference, at least insofar as it's been explored so far. Oh yeah.
That, sorry. So you're comparing the mid blocks to the absorption features?
Yeah.
So you are not fitting the continuum. So if they possible contribute some uncertainty in the result?
Yeah, so basically we force the continuum to reproduce the mean flux over very large scales in Redshift. And this is sort of a way to avoid any like gross continuum errors, basically. So that means that we can't measure the mean absorption because we're forcing it to match quasar measurements. So, you know, in the future we could look at, if we relax that assumption, do we believe that we can measure the mean absorption? But so far we've taken the tack that that's been well done with quasars, and we're more interested in finding sort of the phase, you know, the locations of structures.
So I had a couple of questions. First, there have been some recent narrowband Lyman-alpha surveys that have suggested a correlation between strong Lyman-alpha emission and filamentary structure. Is that something you looked into?
We haven't looked at that yet. So we have just started to look at Lyman-alpha equivalent width versus the overall overdensity, but we have not categorized the map into, say, filaments and nodes and that kind of thing. There is a literature on how to do this and break the map into different kind of, you know, based on the topology and connectivity, and so that would be the next step. That's really interesting that you pointed that out. Yeah, that'll be one of the next things to look at, I think.
Another question I had is in your composite spectra as a function of Lyman-alpha strength.
Mm-hmm.
I noticed that the one with strongest Lyman-alpha also seemed to have pretty strong interstellar absorption lines.
Let's see.
Which is opposite to what we see in Lyman ring galaxies.
Yeah, so
At these redshifts, so I'm just curious if you, well,
I would.
it's not the main focus.
Yeah. So the ones that you saw were not the composites themselves. It's more like each spectrum can be fit as a sum of different templates. And so my best guess is that that galaxy is not typical because in the stacks, as you mentioned, stronger Lyman-alpha has monotonically weaker interstellar lines. So I may have picked a weird example, I guess is my main, because the stacks don't show that. They show the normal trend. Yeah.
These proto-clusters that you're finding, are they just overdensities in H1 and mass, or are they also overdensities in galaxies? I mean, are they sites where you expect a cluster to form, or they already have galaxies in them making stars and doing things?
Yeah, so far it looks like a mix. I mean, some of them are clearly very overdense in galaxies. Others of them are not. However, that requires a little more work to get at because you can also, there's a matter of sampling. Sometimes you're just going to not have observed the galaxies inhabiting that structure. And so we have to do some more work now on the statistics of it to see whether, how many sort of galaxy pore overdensities we would expect to find just because of random sampling versus what we actually see. But I guess preliminarily there are several that seem kind of weirdly devoid of galaxies. The other thing is that we're only getting redshifts for very particular, like pretty bright UV emitting galaxies, and so as we saw, some proto-clusters are very rich in obscured, highly star-forming things or whatever, and so it could be that you're kind of missing the main story in some systems. I mean, we don't know that, but that's something to be determined by more follow-up.
So you've made this is a kind of a unique way of mapping at least that part of the universe, and you're doing it with gas, which is independent of the galaxies, and there are a lot of things it's already taken a ton of work and listed a bunch of things you'd like to follow up on. Let me ask about another one.
Sure.
How many quasars are in this volume, or AGN are in this volume?
So for quasars, we have spectra of about 100 right now, and we're about halfway done. So it's about 4 or 5% of the total sample. AGN are probably similarly common, but I can't think of an exact number for that right now.
As you know, there's some interest in figuring out the way in which the ionizing photons from a quasar are emitted.
Yeah.
Presumably that would show up in your maps as a modification of the neutral hydrogen.
Yes, so that's very interesting. My impression is that, although you would know much more about this, is that our resolution is kind of at the limit of, it's kind of like 1 megaparsec. Is that adequate to see the proximity zone?
It depends on the quasar, but
it can be, yeah. So we should do that. And another problem is that we don't have very good redshifts for all of these quasars because they're UV based, and that they can be off by like many thousands of kilometers per second. But for a subset, if you had a good infrared redshift or something, then that would be a really cool thing to look at. So we should probably try to cull out that subset.